Yeah. Okay. Hi, everyone. Can you see if I need to? Can everyone hear me all right from here? Okay, great. Yeah. Let everyone get settled. So if you're looking for Angela's talk, she is in the other building. So now's your chance to sneak away. All right. Hi, everyone. I'm Sarah Smith. I'm a research scientist here at Berkeley Lab. And since I joined the lab about 10 years ago, I've been working on topics related to load flexibility. So been engaged in our demand response potential studies that we've been doing for the CPUC, which and our ongoing line of research on dynamic pricing. And then since CalFlexHub was initiated a few years ago, I've been leading a task related to analyzing the potential impacts and the value of these different technologies that are being developed. So kind of looking ahead to the future, if these technologies were to be widely adopted and commercialized, and see what we can learn from that. So I think we can maybe dive into the next slide. So yeah, as I just mentioned, we want to look at these early stage technologies, or technologies that are at various stages of development, and look ahead and see what is the potential customer base for them to be adopted, what loads are they targeting, and based on some theories about what these price signals might look like. We don't know exactly, but based on that, what might the load impacts be, the bill savings to customers, and kind of the overall costs and benefits. So this slide kind of gives a summary of our methodology, all the different pieces of the puzzle that we're trying to put together. And I guess I'll kind of quickly walk through them. So for each technology that we're evaluating, again, we have to think about the customer base. So what types of buildings is that technology well suited for or targeting? What end use loads? So maybe it's just a one load like an EV charger, maybe it's multiple loads, heating, cooling, water heating, that all need to be considered. And then thinking about the costs of putting that technology in at those sites. So we've, in some cases, been talking with the technology teams to understand the current costs of those devices, and in other cases, we're using kind of standard, previously existing assumptions from our other lines of work. And then we also, because we're doing this kind of high-level, wide-ranging modeling framework, we can't really get into the very specific, physics-based simulations of each one of these technologies. We have to think about the performance at a higher level. So we parameterize the performance into a few key metrics to represent the technologies based on what window of time they could shift energy across. So is it something like an EV charger that could maybe shift load, overnight, or is it something like pre-cooling with a thermostat that might have a narrower band of that flexibility? And then we think about the depth of the load shift that's possible. So when you ask the technology to shed load, what fraction of that load do we think could be moved out of those high price times? And then some parameters to represent the losses that might be involved, particularly with the thermal technologies. If there's a pre-cooling or something that might require a higher amount of energy, so we represent that in the model as well. And we pair all of those assumptions with existing models for baseline loads in California. So again, this leverages the work we've been doing for CPUC. We have load shapes for what we call customer clusters that are disaggregated at the end use level. And that gives us a lot of variety in the representation across the model. And then as mentioned, we have some different price scenarios. So in the results I'll show you today, we were using a 2019 kind of CalFuse inspired price signal that we had worked with CPUC to develop for some of our research with them. And then we also have some scenarios where we take the value of energy from the avoided cost calculator, so that hourly avoided cost stream, and run that through as a price signal as sort of an alternate representation. And yeah, so I think I have a couple slides on some of the result, kind of maybe refreshing you on some of the results that we found over the last year or two of this work, and then newer insights we've gained from diving into those results. And then I'll talk a lot about, or a bit at the end, about what we're working on right now and kind of improvements that we're making to this analysis. Okay, so this slide captures, also I hope you like bar charts, because pretty much the whole rest of the deck is bar charts, but if you get dizzy, just listen to my voice. So these results show these, again, really high level across the board. If everyone adopted this technology and they all responded in the way that we're modeling, what type of high level load impacts might you see? So on the left and right, or on the two on the left, we have what we call effective DR. So these technologies we do assume are responding day to day, hour to hour to these price signals. But as a way to communicate the depth of that price response, we kind of look at it and say, if this was a DR resource and you were seeing how much was shed in the peak hours, how would you quantify that in those more familiar metrics? And so you see a wide range of potentials here. And you see some differences in what has a lot of shed potential and what has more shift potential. So shed potential is looking at hours when the system net load is peaking, whereas shift is looking at the hours where the system net load is having very steep ramps. So you'll see more of the orange, the water heating and the heating, and even the EVs contributing to that shift potential, because those are year-round loads who can help out in the spring with those steep ramping periods. Whereas on the shed DR side, it's very cooling driven. Cooling is really, the big resource there. And the magnitude of these bars is very much driven by the breadth of the customer base that they are able to target. So again, we're looking across the board if everyone had this technology. So something like a residential technology, we're saying, if every single home had the smart thermostat, what might that look like? So that gives you the magnitude of that effective DR potential. And then here we work with our colleagues at E3 work with us on this research, both doing some of the load response modeling as well as the valuation. So kind of system avoided cost valuation. So this gives you the dollar amounts of the grid benefits and where those benefits are coming from. So avoided generation capacity, transmission distribution are the main drivers of that. And again, you can see across the different technologies, there's a different mix of, the timing of when those resources are available affects where they provide the most value on the system. Okay, and then the next slide, we can look at some more results. So that captures the load and the system impacts, and then we can look at the customer level and say, based on their load impacts, what would that lead to in terms of bill savings? Again, on these hypothetical rates that we hope are somewhat representative, but we don't know yet. What would the bill savings be? And then we can compare that to what the technology costs to look at the value proposition to the customer. And so, of course, one way of looking at that is the payback period. And on the left, you see the averages for all the different technologies, 2 different price scenarios for each technology. And you can see here, again, there's differences based on what end uses are being targeted. So the avoided cost-based price signal is very concentrated in the peak summer hours. And so cooling technologies do really well on that signal because they're able to they have more coincident load and are able to move load and save a lot of money. The dynamic retail price, which again was that CalFuse inspired tariff, has more fluctuations throughout the year. So the year-round technologies, the pool pumps, the EVs tend to do better on that price signal. So a lot of uncertainty there. And underlying each one of these averages is a wide, sometimes very wide distribution of payback periods. So again, we have these different customer clusters that all have different load shapes, load kind of quantities. And some of our costs scale or with the building size, other costs are per site. And so you can end up with very different value propositions across that potential customer base. So, last year when I presented here, I think I had maybe 10 minutes at the symposium. I threw up some of these figures like on the left with these averages. But what we've been doing since then is trying to delve into this range and say, these averages are maybe being pulled up by customers who just aren't well suited for the technology. Maybe their load is very, very small. And so, how can we get a better sense of what the value proposition is for, customers that maybe we could target or kind of see more value with. And so on the next slide, I'll show kind of getting into that way of thinking. So here we've done customer segmentation, and we've looked across that whole range of customer clusters that we model, and we say, okay, who had a payback period of 5 years or less? And we call that a short payback. Maybe others would think, that might be long for some specific customers, but for this analysis, we have the breakpoint at 5 years. And then we said, in the blue category is all the customers that the technology paid off over the lifetime of the technology, but it was above that 5-year threshold. And then lastly, the customers who, the technology didn't pay off in the way that we modeled it. So you can see here some technologies, and the results here are for the avoided cost-based price signal scenario. So there would be a different, potential mix depending on what price signal we were modeling. But you can see here with the like the smart thermostats, for example, or the commercial energy management systems, which also are targeting the cooling loads, you see a mix of customers who fare better or worse on the technology, and then other technologies are kind of more concentrated in one bucket. So with this analysis, on the next slide, you can see some of the things we're trying to learn from this bucketing. So if you look at all the customers who had a payback period of less than 5 years, and if you thought that, a 5-year payback period was the acceptable, our goal of, we'd like everyone to at least make their money back in 5 years, then you can calculate how much customer surplus is there from people who had paybacks of 1 or 2 years. So there's a dollar amount associated with that. And then on the flip side, there's the deficit from customers who had the longer payback periods. And so, this is really exploratory analysis. We're trying to figure out different ways of wrapping our head around how different customers are affected and what that means. And so the thinking here was maybe there would be, programs that could be designed or ways to leverage that surplus that some customers are generating to support customers who maybe aren't as well suited to the technology, but we would still like them to, adopt it. And then I think I have one more slide on these insights. Then the other thing we can do with this analysis is say, again, if we see that 5-year payback period as a target, we can look at the upfront, the technology costs we're currently assuming and back out, again, based on the bill savings we've modeled, how much would that cost need to come down in order to hit that 5-year payback period? And so, of course, there is a wide range of bill savings across the customer base. So that cost target will be a bit, and technically would be different for each customer. But again, looking at these buckets of customers, we can see a lot of the technologies, like the residential EV chargers, maybe only needing to come down 15% or so in cost for everyone who was in that long payback segment to enter that short payback segment to get that 5-year payback period. Whereas other technologies would need, maybe a 60 or 70% cost reduction to hit that. And then up top is if you really wanted to get everyone, if you wanted to get those small buildings, if you wanted to get, all those customers who previously weren't having any payback period in the original analysis, how much would the cost need to come down? So you're seeing, the 80, 90% cost reduction targets there. So these are some of the different ways we're learning to digest and look at this data. And that was a lot of the effort that we're doing kind of over the winter and the spring of this year. And I think I have one more slide. Oh, yes. So what we're doing now is revisiting all of this modeling, going back through the assumptions, working with some of the technology teams to improve the analysis, because like I said at the beginning, sometimes we were carrying over assumptions from previous studies that might not be exactly tailored to a given technology. And even where we did work closely with the technology teams at the beginning of CalFlexHub, it's been a couple years now, so things have changed. So for example, the Smart Fans project, they gave us one cost assumption at the very beginning of the project, and we've since heard from them that now they would put that cost at about a third of what they had originally said. And then with the large office model predictive control project, as an example, it's been mentioned both in Marianne's remarks as well as in the prior session. We can see from the testing results how that technology has been performing, and we can use that to improve those parameters I was describing. So this is a pre-cooling or a cooling technology that I believe we had assumed, could pre-cool maybe over a 4-hour window. But as they've shown, at least in this marine climate that we're in here at Berkeley Lab, they're pre-cooling, all the way down at 3, 4 in the morning, and then being able to reduce load pretty much for the rest of the day. And so we can model that technology with a much larger shift window now and see how that changes our results. On the flip side, when we modeled that technology, we thought, oh, it's one controller, it's some software. We put in a quite low cost that we have since learned is very much an underestimate, that there's a lot of commissioning involved and a lot of labor needed to get those buildings set up to do this, at least in the current state. And so we're also working with them to better represent those costs. And then, we're working with some of our lab colleagues that are working on the water heater technologies to, again, improve the cost and performance assumptions, but also for teams that do have simulation capabilities and do have models that better represent the physics. We can see how our high-level models compare to that and try to better align with their results. And then I'll also add one of the biggest changes that we'll see in our next round of results is new price scenarios. So I've mentioned several times there's a lot of uncertainty in the prices. We did a couple of scenarios, but both of the scenarios we did before were based on the 2019 electricity costs and the 2019 kind of system load shape. I think we all know from looking at our bills that electricity costs have changed a lot since then. We continue, expect some level of continued, increase in electricity costs over the next few years. And so for some of our work for the CPUC, we have forecasted these. We've done a kind of hypothetical projection of what these price signals might look like in 2030, both considering how the cost of electricity has risen and considering how the system load shape is going to look very different. As the duck curve gets deeper and deeper, we'll have more varying shapes in the day and potentially a lot more opportunities to save money. So we'll be able to incorporate those new 2030 price scenarios into our new analysis, which I think will strengthen the value proposition for a lot of these technologies. So lots more to come, and definitely look forward to working with you all on improving this analysis and sharing any insights we can that will be helpful to your work. So I think I've got about 10 minutes for questions. Cool. Yeah. Yeah, Justin, please.
Tristan DeFranco with Skycentric. So smart fans had huge bar graphs. What's a smart fan?
Oh yeah. So I don't know if anyone from the team is here. It's the Big Ass Fans is the technology provider for that project. And it's a fan that has a controller that the idea is that it can switch on when you're trying to shed the cooling load so that you can, even if the set point in the home is, or in the building is rising, it can maintain comfort to the occupant. So by turning on the fan, you can let the temperature ride up a bit higher without the occupant being affected. Yeah, and so at the start, so it can go the way we model it here. It can go into any home that has a cooling system. It has, the ability for them to turn off the cooling load for a few hours is the way we've modeled it. And I think at the time that CalFlexHub started, they were making them as sort of integrated. You had to basically replace the whole fan and put in this fan that was the smart fan. So it was a higher cost. But I think since then they've modularized the controls. So that's why I was mentioning the costs, we believe, has come down quite a bit. Yeah. Yes. Yeah. And are they testing and yeah, we did include some commercial buildings as well and tried to figure out, how many fans would you need based on how big the building is and try to incorporate that.
Yeah, just as a quick follow-up, it seems, especially in residential, that you would need fans in every room. I mean, it's just this huge outlier. So it would really be interesting to understand, what's this gift from heaven kind of thing.
Yeah. Well, and I think that another thing that gets into is, we're looking very much at the technical potential. Again, if everyone did this, but there's in the other talk that's going on right now, Angela and the Task 2 team, they are looking a lot more at the customer experience and the behavioral things, and people might not want a fan in their room or might not like the way that fan looks or whatever. And so you definitely need to take that into account for each one of these technologies, kind of adoption trends and things like that. It's not just about the economics for sure. Yeah. Joe.
Yeah, but I didn't get to go to the large office MPC presentation, so I have at least two questions about the picture you've got up there.
Sure.
What are the internal temperature constraints that allow so much pre-cooling at 3 a.m, and how much of that 3 a.m. stuff is really just smart use of an economizer?
Yes, yeah, it's. I'm looking around to see if that team's in the room, just so I don't speak out of turn. But yeah, in the second kind of row of the figure, you can see the temperature thresholds, and it's hard to tell, but there is a baseline black line and then a green MPC line, and you see a bit of pre-cooling throughout the first half of the day, and then a little bit of that higher temperature, but it's a pretty modest change. But you're exactly right; it's a lot of free cooling that the algorithm was able to make use of, being in Berkeley and being this climate. Yes. Yeah, I don't know where the mics.
Oh, yeah.
You want to do? Okay.
Oh, we have two from our remote attendees. The first one is, in your modeling, does it account for California's fuel mix and electrification scenario today, or California's generation fuel mix and electrification scenario tomorrow, i.e. decarbonization of end uses and generation?
Yeah, it's a good question, and it's a bit of a patchwork in the analysis that I was showing, because we did want to look ahead to how end uses are changing. So being able to capture the electrification of heating and water heating, and EVs especially. So the load shapes we used were from our 2030 scenario, or the forecast again that we do for our DR potential studies. So that was 2030. The avoided costs streams that we used for the valuation, that was also the 2030 forecasted scenario. But again, the price signal was what at the time we did this analysis, we didn't have that forecasted. So it was that 2019 price shape. And so again, with our newer runs, we'll be able to align everything to a 2030 scenario. But to answer, yeah, I wouldn't say that represents, I would say more of a business as usual, especially when it comes to things like electrification. We developed these forecasts around 2021, I would say, based on 2019 data. And so we're definitely due for an update of those underlying load models and taking into account some of the more recent trends and trying to do more scenarios of end use decarbonization.
And the next one, the commenter had a question about today's results and how they compare to prior results, specifically the water heater customer surplus estimates. Have they changed drastically in either direction?
Yeah, we stay tuned. We're not sure quite yet what those results are going to show. I think we'll see, yeah, as we update the various pieces of this puzzle, I think we would definitely expect to have more electric water heaters than what, again, was modeled, when these forecasts were originally developed. So that would be, an increase in the potential. There's also a bit of, what's being represented as the electric resistance water heating versus the heat pumps. That's something that wasn't ever separated out in our load modeling before. We model at the end use level, not the equipment level. So trying to think through how do the baseline loads of those technologies look different, and making sure that, if a technology is targeting the heat pumps, that we are representing what it can do, for those devices specifically. Yeah, and I think there's, we'll see. Yeah, thanks. I think, we can probably take one more.
Thanks. I'm really struck by your first figure with the net present value for savings for the grid.
Mhm.
And 2 points. One is it looks like most of it is generation savings and then transmission and then distribution. So I'm wondering in your modeling how much you really looked at how much shaving peak load could decrease investments in distribution infrastructure.
Yeah, it's a really good question. And I would say in this analysis, there's representation of these costs in the avoided cost calculator, which we have here, but we're not saying, at a circuit level or at a granular level, where might there be capacity issues, and, kind of more so understanding that granularity to better capture those savings. We do have colleagues at the lab who are, diving really deep into distribution system modeling and looking at the impacts of electrification, of EVs, of load flexibility. But it's a very, nuanced case by case. Every circuit's different. And so I know that some of the utilities we've talked with are working on doing their own circuit level models and thinking about where they're planning upgrades and seeing if they could apply the type of modeling we do here and in our DR potential study at that circuit level. But it's not something that we've done.
And then the payback periods are based on, current retail rates or
what for the electricity prices?
When you calculate payback period for the different activities, are those based on current retail rates?
Yeah, well, they were 2019 dynamic rates that were kind of designed to be revenue neutral to the retail rates at that time. Yes. Yeah. And we'll be moving towards our forecasted
hourly rates. Okay.
Yeah.
And I guess the point I wanted to make is, as sort of was alluded to in the previous panel, the rates available to customers don't even differentiate. I'm on an EV rate, and it's the same from midnight to 3 p.m. There is no crediting for load shifting to midday. Finally, it makes me think, if you look at the potential for grid benefits, how is that reflected either in decreased prices to customers or increased payback to the people who are making it available?
Yeah, those are good questions. Definitely, the kind of vision of the load management standards and, all these efforts are going on is to move away from these, very coarse, blocky time of use rates and have something better. And then, how those savings materialize, I think is a really good question, is it reduced RA requirements? Is it actual deferment of capacity? Really understanding where that savings is going to come from, I think is an ongoing question, because that's the only way that it can be passed on to customers. Thanks. Okay. Do you want me to? Okay. Oh.
Just a quick comment on 2019. Retail commercial rates in California are up 70% since 2019. My customers pay 70% more than they did in 2019. So a lot of these things are more cost effective, sadly.
Yes, exactly. Right. Thank you, everyone. I think, do you want to transition? Thanks.
Thanks so much, Sarah. So what you're seeing is we've been continuing to evolve the techniques that we use to value the technologies. And again, customer value, grid value, societal value. And we're continuing to evolve these numbers over the next year. So look forward to a year from now and we'll have sort of the final word. So we're at lunch. And I want to thank everybody for joining this morning. Lunch is across the way. The folks that are over there have the first dibs at the sandwiches. And we're going to be back here at 1:30. So go ahead and it's the third floor, I think it is. And there's a big terrace. So hopefully there's some air conditioning and some sun so you can have your choice. Thanks.